yeah, this is huge. What we're going to show in this video, and it's going to be a tough one, but for those of you that wanted to know why we can go from this differential equation to the population equation, which is y equals L, the carrying capacity, all over 1 plus CE to the minus KT. For those of you that wanted to know why or how we go from here to here, you got it. Hopefully you'll never have to do this in class, but let's dive. It's a gnarly integral. So we're going to solve this differential equation to get our population equation. Makes sense. We go from the rate at which the population is changing to the population function. This requires some serious manipulation. So what I've got going on here is I've got my normal equation right there, and of course I wrote it as 1 plus. It should be 1 minus, right? So we go from 1 minus y over L to y equals L over 1 plus c to the minus kt. Now, we are going to separate variables, but before we do that, I'm going to rewrite this as one common denominator, and I'll explain how I got there. 1 is L over L, so that'd be L minus y over L. Okay, so we have that. Now we can separate variables a little bit neater. So I'm going to bring all the y values over this side, and really the only y values or the only non-y values would be k to be left on the right. So I've got dy over, and follow me on this, you've got y times L minus y. The L minus y goes to the denominator, so does the y, and then the L that's in the denominator will go in the numerator, basically multiplied by L over L minus y times y, right? And then on the right side you get k dt. Whew. Right away it's like, what? It gets worse. Of course, I mean better. How the heck do we integrate that left side? The right side's fine. The right side we'll just integrate. It's kt plus c. That's not bad. The left side, though, we look at that and we're like, I don't know how to integrate that. L's a constant, just like k is, but u sub, no. We're going to add 0. Watch this. So we've got the integral of, I'm going to rewrite the top as L plus y minus y. Actually, I'm going to do it in a separate order just to make it a little bit quicker so we don't have to rewrite it. I'll do L minus y plus y. You might be like, you can do that? Sure. All I did right there is I added y and subtracted y at the same time, which is adding 0, which doesn't change what L is. By doing that, look what we can do. We can split up this integral, or that integrand, ly all over y times L minus y, plus y over y times L minus y. This is going to allow us to split up the fractions. You've got to keep the denominators the same, but the numerator can be split, and that's equal to kt plus c. All right, it's tough. The L minus y's divide out, so you get the antiderivative of 1 over y, plus these y's divide out. Oh, isn't that pretty? 1, so that's going to be plus, and then you've got 1 over L minus y. Ooh, my goodness. Gracious me. Okay, then we're going to integrate. Remember, L is a constant. When you integrate 1 over y, that's not bad. That's the ln of the absolute value of y. This, be careful. You'd think it's plus, it's minus, and I'll explain why. Ln of the absolute value of L minus y. When you take the derivative of this, you'll get 1 over L minus y times negative 1. That negative is there so that when the times negative 1 comes out in the derivative, we end up back to the plus. And that's equal to kt plus c. Next, let's join up ln. Our goal is to solve for y now. I told you this was rough, but we got this. We got it, and it's beautiful. So if you're still with me, you inspire me. Let's keep going. Y over L minus y. We use log rules there. Whenever we subtract natural logs, we can divide the arguments. Okay, getting there. Still far cry from that, I'm sure. Now we're going to exponentiate both sides to solve for y. When we do that, the ln drops, and we'll go here. What we are left with is the absolute value of y all over L minus y, which is equal to e to the kt times e to the c. Remember that these are now exponents, the added exponents here, so we end up multiplying the bases. To get rid of the absolute value, we end up with plus or minus e to the c, or just capital C. Some people will use a b. I've seen that in some textbooks, pretty gnarly. Now from here, we're almost done. We got to solve for y, so let's get rid of the L minus y in the basement. So that's going to be ce to the kt times L minus y. Okay, getting there, right? Getting there, not quite. So now we got the ce to the kt. I'll divide that on both sides. just to get that away. And that's equal to L minus y. Now remember, we want the y's together. I'll add y to both sides now. Oh, look at that. You might be like, well, it's not quite this. We'll get there. Is equal to L just on the right side. Now let's think about this. This right here, CE to the KT, is the same as taking that exponent and making it negative. This is gnarly. A lot of nifty algebra in this. CE to the minus KT is equal to that. It's the same as dividing by all of this. And you might be like, how can you just put the C up there? It's a constant. It doesn't matter if it's in the numerator or in the denominator. It doesn't. It's just some constant. It could be up here or down here. Okay, so now I'm going to factor out what I want to solve for. Y times 1 plus CE to the minus KT. Oh, it's about to happen. All of a sudden, it comes together. We divide both sides by the number times y to isolate y. And you get L over 1 plus CE to the minus KT. Oh my word, what a trip. That was fun to go on it with you. We'll leave it at that. That is why and how we go from the differential equation, the logistic differential equation, to the population equation. I will see you next time, hopefully in the exercises, for logistic growth. Peace.